Hello and welcome back to a new session, and we are going to continue our discussions on implementing single purpose computers. I am your instructor Dhananjay Gadre. In the last lecture we covered some ground to understand the components of a single purpose computer, namely we need a sequencer and we need data path. The sequencer is nothing but a finite state machine. That finite state machine could be implemented either as a Moore machine or a Mealy type of finite state machine. It does not matter. The data path elements will be determined by the requirements of this single purpose computer. So, to illustrate this idea, I am going to present to you a single purpose computer which will play a game which we call as a dual dice game. Before we start implementing the game, as we always do, whenever we have to implement something, the first and foremost task is to set down on a piece of paper the requirements. Unless you know what you expect out of that implementation, things will not move forward. And so, here is the problem statement. We are having a game where there are two dice that we roll. Now, when we roll a dice, the number is between 1 and 6. When we roll two dice, the purpose is actually to sum the output of these two dice, and therefore, this dice will produce numbers between 2 and 12. Based on this sum, we will take certain actions. So, when we roll the dice, the two dice, the number displayed will be displayed, the sum of these two dice will be displayed. If the sum is a value between 3, 6 or 9, that is, if the sum of the two dice is 3 or 6 or 9, the player wins and the game terminates there. If the sum is 2, 8 or 11, then the player loses and the game ends again. In case the number is anything other than these, which means if it is 4 or 5 or 7 or 10 or 12, then the game proceeds to the second stage, and before proceeding to the second stage, it stores the current number that was received, which means that number had to be one of these numbers. In the second stage, the user is prompted to roll the dice again, and the new number is displayed on the 7 segment display together with the old number. You would like to know what your previous number was, because in the second stage you are going to take some decisions based on the previous value of that number also. And so, if the old number matches, the new number matches the old number, you win. On the other hand, if the new number is 3, 6 or 9, then you lose. Else the current value of the new number that you got becomes the old number, you store it and prompt the user to roll the dice again, and you stay in stage 2 till a decision comes out. Let me draw for an end user what would the game look like. So, we want a system which has a mechanism to roll the dice, and we do not have a physical mechanism where we are shaking it, and instead we have a switch with which we can simulate the act of rolling the dice. So, when I press the switch, it is like I am rolling the dice. So, dice is I am shaking the dice, and when I release the switch, it means that I have thrown the dice and you see the two numbers that come out. And so, I would like to display them on I will need 4 7 segment displays, because I have a number which can be more than 10, and I have to display two such numbers, one for the current stage and maybe if you happen to go to the second stage. So, I have 4 7 segment displays here. Now, how does the user know that the game has been won or has been lost, or the game has gone to the second stage? So, we have to use some indicators to indicate. So, let us say that we use a LED which is appropriately labeled. So, this could be win, another LED could be to indicate that the user has lost, lose. A third LED, in case it is neither win nor lose, then it must indicate that now the user has to press the switch again. So, we call it play again or PA, play again. You could also have a buzzer to sort of indicate some result. You may also have some LEDs to indicate are you in stage 1 or have you gone to stage 2 and so on. And of course, these numbers, so this could be old numbers and these could be the new numbers. This is the user interface to the system. Now, we have to design everything that goes in here with the help of logic circuits, which will be partitioned in two halves, two parts. One will be called the sequencer. What will the sequencer do? It will essentially follow the rules of the game. It will prompt the user to press a switch. When the switch is pressed, it will debounce that switch, and then it will roll the dice. When the switch is released, again it will debounce the switch, and then it will stop the dice, look at the numbers, and there are many ways of processing that information. Maybe you have two dice and then you use a arithmetic voltage number adder to add the two numbers, or you can take an alternative approach by saying let us make a counter, a single counter which counts from 2 to 12. So, it goes from 2, 3, 4 up to 12 back to 2. Now, of course, there is a difference in the way these numbers will appear in these two approaches. If you use two counters which have a number between 1 and 6 for both of them, and then you use a adder to add these numbers, the probability of some of the numbers will be more than the probability of other numbers in this case, compared to a solution that you can choose that you have a single counter which has a number between 2 and 12, because in this case the probability of each number is same, whereas in the earlier case of using two counters, some numbers will have higher priority. And there are again various methods of improving the probability of certain numbers even in the single counter method. So, this is the overall block diagram. Let us look at what are the kind of elements of data path that we may require. We would require a debounce circuit, because there is a switch which is a mechanical switch in nature, and when the user will press and release that, it will produce switch bounce. We will need some counters to implement the random number generators. As I mentioned, it could be a single counter to go from 2 to 12, or it could be two counters each of which have a number from 1 to 6, but then you will require another logic block to add these two numbers. You may require comparators. Why? Because now you have to decide what is my number, what is the result of that rolling of the dice. Is it 3, then you win. If it is 6, you win. If it is 2, you lose, and so on. So, that is best done using comparators, so that you know what is the result of that. Then you may want to, if you in the stage 1 you do not win or lose either, then you have to go to stage 2. For that you will have to store the current number, which you will do using a latch with enable signal, and of course you will require decoders to display the numbers on 7 segment displays. So, broadly these are the building blocks, the data path building blocks that you will require, and let us now look at the representation of these blocks with their interconnection to evolve from our single block diagram, user level block diagram, to a more detailed interaction between the circuit elements. Here is the complete block diagram, which involves elements of the data path as well as the single block which represents our finite state machine. So, I am going to zoom on this part of the circuit to first talk about the finite state machine. So, here as you see, the finite state machine produces two types of outputs. If you remember, let me draw it for your easy reference, that a state machine will produce two sorts of outputs, two types of outputs. One which could be for global output. So, these are global outputs, and it would produce outputs which are control signals to the data path element. So, these are control, and it does that with the help of asynchronous inputs together with inputs coming from the data path elements, and so these are status inputs. So, you have to design a finite state machine where the inputs are the asynchronous inputs as well as the status inputs, and the output of such a state machine will be two sets of outputs. One is the global outputs and the other will be control outputs which go to the data path, and so we must see both these sets of outputs together, and this is what is being done here. If you see, if you look at this signal, win, lose, play again and buzzer, these are global outputs. You also have state LED 1 and state LED 2, this indicates whether you are in stage 1 or stage 2, and you have other control signals, which is to display, you want to enable or disable the display, or you want to enable the latch, and you have another signal which is the control signal for the counter. Okay. These are the global and intermediate outputs, and then you have some inputs coming from the state diagram, the data path, and these are when the values are equal, previous and new values are equal, or if the current value is equal to 2, 8 or 11, we have labeled it as a single signal EQ 2, 8, 11, and another signal which indicates whether the sum is 3, 6 or 9. And the rest of the other asynchronous input is the reset, to reset the circuit to begin from scratch, and the switch, which is the actual switch used to interact with the game. Now, let us zoom this part of the circuit to see how the various data path elements are required and what functions they serve. So, the first element of data path is a counter, which produces, is a 4-bit counter, it produces numbers between 2 and 12. These go into the 7 segment display control circuit. It is a 4-bit binary number and it is converted into a decimal number which could be anywhere between 2 and 12, and it will be displayed either on these 2 digits or these 2 digits. Then in case you do not win or lose, you have to go into the stage 2. For before that you do that, you have to store that number, and so it is stored into a latch. It is a 4-bit latch with enable signal, and then if the number, you have to find out when you have rolled the dice, is the number equal to 3, that you do with this comparator, or if the number is 6, you do it with this comparator. The two inputs of the comparators are one which is coming from this counter and the other which is a fixed value of 3 here, 6 here and 9 here, and these 3 outputs are ORed together to create a single signal called EQ 369. So, if EQ 369 is 1, that means your sum was either 3 or 6 or 9, and the state machine can take an appropriate action, that is to declare either win if you are in stage 1 or lose if you are in stage 2. Similarly, the same number is going to 3 comparators here, one where the input is 11, second where one of the inputs is 8, and the third where this second input is 2, and it is being compared with the output, current output of the counter, and if this output, which is the OR of these 3 comparators, if it is 1, that indicates that your number was either 2, 8 or 11, and again this signal is going to the finite state machine to indicate to the finite state machine the result of your of this roll of dice, and for it to take appropriate action. In case you in stage 1 you neither win nor lose, the finite state machine will generate a control signal to capture this input, and it will be available at this point, and it will be compared with the current value of the, when you roll the dice again, this current value is available here also, and if these two numbers match, then it is called EQ previous, and this goes here again to the state machine as a control, as a status signal, and the state machine will decide what to do with that number. Apart from that, here are the 3 LEDs for win, lose and play again. Here are 2 LEDs to indicate the stage 1 or stage 2 of the game, a buzzer to beep whenever certain action is taken. So, this is the representation. Now, we are still not anywhere near completion. We have to now decide what are the states required in the finite state machine. So, let us have a look at that. Here is the finite state machine. You start with S0, that is your reset state. You wait for a button. If the button is pressed, you go into S1. If the button is not pressed, you remain in this state. That is not being mentioned here, but that is what is being done. If the button is not pressed, you remain in S0. If the button is pressed, you go into S1. In S1 now, in each of these states certain outputs are being produced, and I will show you the next slide where we have made a list of these outputs, and we know these outputs. What are these outputs? These outputs are these various values as well as which consists of signals which are control signals to the data path, and 3 global signals which is win, play and lose, and 2 more global signals which is to indicate whether you are in stage 1 or stage 2. So, all these outputs from the state diagram, state machine are mentioned in each of the state S0 or S1. Now, these outputs are either 0 or 1, but in some cases it is X, which means it does not matter. So, that is a do not care, which would mean that it is okay if it is 0 or it is okay if it is 1. Maybe the previous state would have decided if it is 0, it will remain 0 in the next state and so on. So, those states are mentioned as XX here. So, you go from you are in state S0 waiting for a button to be pressed, you come in state S1, in that you now start a counter, and that we will see when we look at these numbers. Here you wait, here now you wait till the button is released. When it is released, you go into S2. Here numbers are ready and they will be displayed. If the number is EQ 2811 and not EQ 369, you are going to go into state S4, which is actually to indicate that you have lost. On the other hand, if EQ 369 is 1, I should not put a bar on it. If the state 369 is 1 and EQ 2811 is 0, that means you are winning, you are going into this state, and an appropriate output will indicate whether it is a win or loss, and from there you will go into this waiting for the button to be pressed. Else, if neither win nor loss, you are going to go in this state where you are going to request the user to press the button again by the help of LED called play again, and once it is pressed, you are going to go in this state. Here you are going to start a counter, the counter to produce a second random number, wait for the button to be released, and then once the number is generated, you are going to compare it with the previous number. Here if it is equal to previous and not anything else, you are going to win state. This is your win state, this is your lose state, this is your state to indicate your stage 2. If the numbers are not equal, then you go back. If the number is equal to 369, you lose, else you go back and ask the user to press the switch again, you are still in stage 2. Now, to know what outputs are produced, here is a table. Here is a table which indicates the outputs required: stage 2, stage 1, display enable, win, play again, lose and latch enable. This latch enable signal is to generate the enable the latch to capture that number. In state S0, you want the play again. Now, since the LEDs are connected in active low mode, which means the LED will light up when the output is 0, you are only lighting the play again LED. You have disabled the latch, you do not want to capture the number, and rest everything does not matter. The counter is free running, so it is going to keep on running. In S1, you are indicating that you are in stage 2, stage 1, because again it is an active low LED. You have enabled the display, you are indicating that it is neither win nor lose nor play again, and you have enabled the latch, and from here you see each of these stages have indicated the kind of outputs that will be produced. Some of these outputs go to the outside world in the form of win, play again, lose, or stage 1 and stage 2. The rest of the outputs go into the data path, controlling those data path, which is namely the counter and the latch and the display control circuit. This table is required. It will list all the states and the expected outputs, and these numbers as you see here x, 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 0, x, 0 will exactly be here, x, 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 0, x, 0, and likewise you will see that in each of these states we have mentioned what numbers are, what outputs are being produced, what is the state of those outputs. Once you decide this as I mentioned, this finite state machine can be implemented as a piece of VHDL code. All the elements of data path, whether it is counter or 7 segment display or these comparators, can be again represented as VHDL code. So, now you create a single VHDL code where you write down the code for each of these building blocks, finite state machine, the counter, the latch, these comparators and so on, and when you compile that you will get a net list which you can implement in any form. Now, what are the options we have? So, we can implement this net list at in various ways. One common method is to use a programmable logic device, which are primarily of two types. You either have a simpler smaller device called complex programmable logic device, or you have much more denser in terms of the number of gates, you have a field programmable gate array. There are many manufacturers which make CPLD and FPGA devices. One very popular manufacturer is Xilinx. They also provide a software for modeling codes and then targeting their products. They make CPLDs as well as FPGA. They have a software called IAC, which allows you to write and test, compile and download the VHDL code or Verilog code into the target IC, which could be a CPLD or FPGA. So, this is one approach. The second approach could be that given the netlist, you can get a application specific integrated circuit being made. That is another possibility. Now, what we are going to show is how to take the code that we have written, compiled it using an appropriate compiler, in this case the Xilinx IAC, and we will show implementation using a CPLD. This is the block diagram of the implementation. As you see here is a Xilinx CPLD XC9572. It has two switches, reset and the button which is used by the user to interact. It needs a power supply. I am going to come to that. Here is the display which indicates the new number here and the old number here. These are the three status LEDs which indicate win, play again and lose, two LEDs which is stage 1, stage 2 and a buzzer. Now, exactly like we talked about the ecosystem for a microcontroller, and we mentioned 4 elements of ecosystem, namely 1 was clock, 2 was reset, 3 was power supply and 4 was program download capability. These 4 ecosystem elements that are required, essential elements of ecosystem that are required by an embedded computer such as a microcontroller, are also required by a programmable logic device such as a CPLD or a FPGA, and this previous block diagram actually indicates that. Here is a power supply. From the data sheet of this CPLD, we found that the power supply required is 3.3 volts. It also mentions, the data sheet mentions how much current it will consume. So, the power supply has to be appropriately designed so that it can provide that power. The source of the power supply is important. In this case, it was implemented using a USB input, which is 5 volts. You require a clock. So, power supply and clock, and in this case the clock was implemented using a 555 astable multivibrator, because the requirement was not very high frequency. Otherwise, we could have used other approaches, and of course, it requires a reset. So, this is your reset switch. So, in this case there is only one reset, which is the user reset, and power supply and the clock generator. Now, how do I download code into this? Most CPLDs and FPGAs require a JTAG, interface, and so whenever you want to download code into your CPLD or FPGA, you need a mechanism such as a JTAG JTAG interface to download the bit file. Basically, when you compile the code will the compiler will produce what is called as a fuse bit file, meaning the fuses in your programmable logic devices will be set on or off to create the circuit that you want, and this output of a VHDL compiler is usually a fuse bit file that needs to be downloaded into the target device, and for that JTAG is used. So, what we did was tested the circuit first on a evaluation kit. Like we have evaluation kits for microcontrollers, there are evaluation kits for programmable logic devices also, and once the code was found to be working, then an entire standalone implementation was created, and let me show you that. This is the schematic diagram of the CPLD based dual dice game. Here is the power supply. As you see, the input is a 5 volt source. It produces VCC, which is in this case 3.3 volts. It uses a voltage regulator called 1117. The clock generator is based on a 7555 astable multivibrator, and it produces about few kilohertz of clock. We do not need very high frequency clock. Here is the CPLD, which is a XC9572. Various outputs of the CPLD are connected to the various peripheral devices such as displays and buzzers and LEDs, and here is that connector JTAG connector, which is TDI, TMS, TCK and TDO. This is an external connector, external interface. Here is the display, which is a 4-digit 7-segment display. Here is the buzzer. These are the output LEDs for win, play again and lose, and also stage 1 and stage 2, and these are the 2 switches for playing, the user button and the reset switch. This is what we have. Here is the board layout. This was fabricated in my lab on a single sided board. Now, the CPLD itself consists of SMD IC, which has very fine pins, and it is not possible, or it was not deemed possible, to be able to fabricate a circuit to accommodate such a fine pitch IC. And so, an interesting approach, as I had mentioned earlier, was taken to create a breakout board. This is the breakout board. This was fabricated using outside fabrication facilities, and on that, this is actually a 44 pin universal bob, which means any 44 pin IC can be soldered onto this, and at the bottom appropriate ground pins. This is the ground, this is going to be ground plane, this is ground plane. So, appropriate, depending upon which pins of the IC that you are soldering need to be grounded, they are grounded here, here, here and somewhere here. Some of the pins are VCC, so they need capacitor to be connected to ground. So, you see a capacitor here, you see a capacitor here, and you see a capacitor here. So, this pin must be VCC, VCC and VCC, and this is what it looks like at the top and the bottom. This is the actual implementation. This is the top layer. Here are the win, play again and lose LED. This indicates the stage you are in. This is the old number, this is the new number, this is the clock generator, this is the reset switch, and this is the user switch which you press. These are the rules of the game which are mentioned. So, this is the bottom layer of the PCB, which has the power supply, regulator. This is the USB connector, and labels have been put to indicate what it is, who implemented. This is the name of my student who implemented this. It is your prerogative what you want to print. The PCB technique offers you that flexibility, and I hope you enjoyed this lecture. It gave you an insight into how to design and implement single board computers on programmable logic devices. A CPLD typically has much less resources, and so you will have to really struggle with the logic to optimize it. If you have access to a FPGA, which has tens of thousands and lakhs of gates, you will be able to implement much larger designs, but the approach will still be the same. It is an approach which has a sequencer, it has data path elements, and it is left to you to decide what elements of data path are required, how are they controlled by the sequencer, what outputs do they produce, what kind of global outputs they produce, what kind of status outputs they produce. Once you integrate these two building blocks and you model it using VHDL in a single program file to integrate everything, you will be able to implement your own single purpose computers. I hope you found this very useful. I hope you will be able to learn from it and implement your own single board computers. Thank you. I will see you very soon.